Welcome to today's explainer. We're jumping right into Lesson 4, Part 2 on evaluation metrics. We're going to look really closely at exactly how we validate safety at our 3D printed upper limb splint startup. Because look, when you're engineering medical devices, you absolutely cannot just guess that your product is safe, right? You need mathematical certainty. So we're going to explore the rigorous predictive modeling and evaluation frameworks that literally stand between a manufactured biomechanical device and the patient who desperately relies on it. Let's get into it. Let's kick things off with a pretty staggering number, 5,000. That right there represents the annual demand for new 3D printed biomechanical devices, specifically prosthetics, in Colombia alone. Just sit with that for a second. That is 5,000 individuals every single year who need reliable, safely engineered structural support just to go about their daily lives. It really gives you a clear idea of the massive scale and, frankly, the profound human impact of localized manufacturing. We aren't just printing plastic here, we're printing independence. But when the scale is that large, our quality control algorithms have to be absolutely flawless.
So, here's our roadmap for today's explainer. We'll start with the catastrophic false positive, then move to the confusion matrix, precision and recall, the F1 score, and finally, wrap up with the ROC curve and AUC.
All right, Section 1, the catastrophic false positive. We've got to begin our deep dive by understanding the absolute worst-case scenario. Because, honestly, before we can even talk about success, we have to precisely define what failure looks like. For our upper limb splint startup, predicting that a structurally defective 3D printed part is perfectly safe, what we call a false positive, well, I want to be incredibly clear here. This is a catastrophic event. Imagine if our algorithm looks at a splint with, say, a microscopic fracture or maybe some poor layer adhesion, and it rubber stamps it as safe for clinical use. That directly harms the patient. The device could literally fail under the everyday stress of just moving around. In our field, a false positive isn't just a bad data point on a screen, it is a physical injury waiting to happen. Moving right along, Section 2, the confusion matrix. To absolutely prevent these kinds of disasters, we have to rigorously categorize every single prediction our quality control model makes. Think of the confusion matrix as our ultimate tracking system for the good, the bad, and the dangerous. In this 2x2 grid, we've got true positives, that's where a safe splint is correctly identified as safe, and true negatives, where a defective splint is rightly flagged and tossed in the recycling bin. But the really critical areas are the errors, right? We have false negatives, where we accidentally throw away a perfectly good splint, which, cost us money, sure. But then we have those false positives. As we just talked about, that quadrant right there is the absolute danger zone.
Okay, let's break this down further in Section 3, precision and recall. From that grid we just looked at, we extract two highly specific metrics that tell us exactly how reliable our quality control algorithms really are. First up, precision. Precision asks a super vital question. Out of all the splints our model approved and shipped out as safe, what fraction were genuinely ready for clinical use? If our precision is low, it means we're basically letting defective, dangerous splints slip through the cracks. In medical manufacturing, your precision doesn't just need to be good, it needs to be exceptionally high. On the flip side, we have recall, which helps us understand our model's sensitivity. Recall basically asks, out of every perfectly printed, structurally sound splint sitting in our inventory, how many did our algorithm actually find and approve? If our recall drops, it means our quality control is just being way too strict, and we're tossing out perfectly good medical devices that could actually be out there helping patients. Which brings us to Section 4, the F1 score. So here's the catch. High recall might come at the cost of those dangerous false positives. Essentially approving everything just to make sure we don't accidentally miss a good one. We obviously can't do that. We need a single metric that perfectly balances the two. Enter the F1 score. It calculates the harmonic mean of precision and recall. Now, unlike a simple average, the harmonic mean mathematically punishes extreme discrepancies. If our algorithm tries to sort of game the system by approving every single splint just to hit 100% recall, our precision is going to plummet, and the F1 score will crash right along with it. This specific formula is crucial because it ensures we never, ever ignore the catastrophic risk of a false positive, while still letting us maintain an efficient manufacturing pipeline. Now for our last metric, Section 5, the ROC curve and AUC. Once we've got our F1 score optimized, we still need to evaluate the model's overall performance across all possible diagnostic thresholds. Basically, we want to see how it behaves under different levels of strictness.
We do this by plotting the true positive rate against the false positive rate to generate our ROC curve. The y-axis here represents how well we catch the good splints, and the x-axis shows how often we accidentally pass defective ones. As we tweak our algorithm's sensitivity, this curve beautifully visualizes that exact trade-off. It shows us exactly how much risk we're taking on for every single incremental gain in production efficiency. Looking at our current benchmark, we've got an area under the curve, or AUC, of 0.749. So what does that actually mean in the real world? It means our algorithm has nearly a 75% probability of ranking a randomly chosen safe 3D printed splint higher than a dangerous defective one. It's a really solid baseline for sure. But listen, in biomechanical engineering, we are always relentlessly pushing that number closer and closer to 1.0.
Next up, grounding the data, mechanical reality.
Okay, now that we have a solid grasp on the algorithms evaluating our devices, we really have to ask, how do we actually define the baseline mechanical ground truth that feeds into these algorithms? I mean, what physical forces are these splints and prostheses actually dealing with out in the real world? To figure that out, we draw from critical biomechanical studies of the human gait. In a healthy individual without an amputation, vertical ground reaction forces are distributed almost perfectly evenly between the left and right sides. We're talking a tiny 2% asymmetry. But in an impaired individual using a prosthesis, the studies show massive force asymmetries. We literally see a staggering 12.5% load difference. This incredibly unequal distribution of kinetic energy is our mechanical reality. And honestly, it proves exactly why our predictive models just have to be flawless. If our devices are absorbing 12.5% more force on one side, a defective part is going to fail instantly. To make absolutely sure our devices won't fail under that heavy, uneven load, we actually simulate energy absorption mathematically before the 3D printer even turns on. We use the Maxwell model, which places a spring and damper in series to simulate exactly how the material is going to deform. And then we contrast that with the Kelvin-Voigt model, which places them in parallel to simulate pure energy absorption. These mathematical models are what provide that vital ground truth data that our machine learning algorithms rely on and evaluate. As you digest everything from today's explainer, I really want you to consider the broader implications here. We started off talking about a 5,000-unit annual medical deficit in just one country. Localized fused deposition modeling, 3D printing, is already stepping up in a big way to manufacture those devices. But think about what happens when you combine that local manufacturing with the advanced F1 score validations and viscoelastic modeling we just walked through. You don't just get a printed piece of plastic anymore. You get a guaranteed, safely engineered medical device. So I'll leave you with this. Consider how applying these rigorous, mathematical, predictive models might completely democratize safe, reliable healthcare engineering across the entire globe. Thank you so much for joining me on this explainer, and keep questioning the math behind the manufacturing.